Ionic compounds. There are lots and lots of ionic compounds. If you look at the Earth's crust, take a shovel and start digging, most of the things you're going to encounter are ionic compounds. They are present in the foods that we eat. They are very stable because ionic bonds are very strong. And so once they form, they tend to stay together. Here are some examples. This is kind of interesting. Light salt. It doesn't mean it has fewer calories than regular salt, because salt doesn't have calories. Our body doesn't get any energy from it. But sodium is a concern if you have high blood pressure issues. And so light salt is a mixture of sodium chloride and potassium chloride, so that you can get the saltiness without as much sodium. And the potassium actually helps your body to manage the sodium better. This is an example of a complicated ionic formula that we're not going to have to deal with in Chem 1A, but some of them get a little messy. So how do we write formulas for ionic compounds? Here's a list of instructions for those of you who like lists of instructions. So write the symbol for the metal ion, the cation, with its charge, followed by the symbol for the anion with its charge. It's really important to have the correct charges in there. We adjust the subscripts on each cation and anion to balance the overall charge, and then we check that the sum of the charges of cations equals the sum of the anions. So all compounds are neutral, meaning you have to have an equal number of positive and negative charges. If the charges don't add up to 0, then something is wrong with your formula. Now that middle step, number 2, is a thing that is a bit tricky for some people, and I'm going to show you a couple of different ways that you can accomplish that. Ionic compounds always have a positive and a negative ion. Otherwise, they're not going to be attracted to each other. The first element in an ionic compound is almost always a metal. The one exception that we need to be aware of is ammonium, NH4. NH4 plus is a cation called ammonium, and if you see a compound that starts with NH4 and it's got something else after it, that's also an ionic compound. That's the one type of ionic compound that doesn't have a metal in it that we're going to need to think about. So the sum of the charges, the positives and the negatives, have to be equal. And then another important point is the formula for an ionic compound represents the smallest whole number ratio. So ionic compound formulas are empirical formulas. There's a couple of exceptions, but we won't worry about those. So we're looking for the smallest whole number ratio. So let's practice here. Write the formula for the compound formed between potassium and sulfur. So we need the formulas for the ions with their charges. So what group is potassium in? It's in group 1. That means it has a +1 charge. So K plus. Sulfur is S. How do we figure out the charge on sulfur? Count backward from the noble gases. 0 minus 1 minus 2. 2 minus. If you're iffy on how these charges work, please ask me during lab, because it's important. This is going to come up over and over and over again. Okay, so there are formulas for our ions. We need to figure out how we can put these together and have a neutral compound. Can I just put one of each? No, because then overall I'm going to have a -1 charge, right? I don't have enough positives. I can't change the charges. All I can do is add more of the ions. So if I had another potassium ion and put this group of 3 things together, would the charges add up to 0? Yes, they would. Another way to represent that is, okay, I drew 2 of those, and so the total over here is +2. I have 1 sulfur, and the total over there is -2. We want these magnitudes to be the same, because +2 and -2 add up to 0, a neutral compound. So I've got 2 potassium ions, and 1 sulfur. So K2S is the formula. You may have learned a crisscross technique, which a lot of students are very fond of, and it works most of the time, and that's pretty good. So there, to get your formula, you're going to crisscross the charges. So you're going to take the 2 from the sulfur, and that becomes the subscript for the potassium. And we're going to take the unwritten 1 from the potassium, and that becomes the unwritten 1 for the sulfur. And we get K2S. That's a quick and dirty way of getting the correct formula. It doesn't really help you understand why. And so I would encourage you to try to think about it in this way. If neither of these is working for you, I can do it with bowling balls or cookies or money. There's all kinds of other things, so please hit me up for that during lab, okay? Any questions about K2S? Let's do aluminum and nitrogen. What charge does an aluminum ion have? 3+, because it's a metal, that's why it's positive, and it's in group 3A. So we learned in chapter 2 that metals in group 1, 2, and 3 have a charge that's equal to their group number. Nitrogen's the nonmetal. What's its charge? -3. Again, counting backwards, or group number -8. So looking at this one, if you like the crisscross method, do this before you crisscross. Are these numbers the same? 3 and 3? They are. Don't crisscross. Just shove them together, right? Okay, guys, we just need one of each of you, and we'll call this ALN. Because if I crisscross, I'm going to end up with AL3, N3, and then I have to simplify the ratio, and I might forget to do that. Any questions? Well, how do we name these? Some compounds have common names, like water, but all compounds have a systematic name. So a compound can have more than one name, but all compounds have one correct systematic name. So to name things, we first have to identify what kind of a compound is this, and so we want to remember that ionic compounds are generally formed of metals and nonmetals. And so here we have examples. So usually looking at the first letter in the formula will tell us what kind of a compound it is. So Na, we find on the periodic table, it's a metal, ionic. Aluminum, a metal, ionic. Calcium, ionic. Magnesium, a metal, ionic. Okay. The one exception is the NH4. So the book likes to categorize ionic compounds in 2 different ways. So I'll mention this even though I think it's a little bit dumb. There's metals that only make one kind of ion, and then there are metals that make more than one kind of ion. And so there's a very subtle difference in how they're named. I prefer to think of it just as the difference in how the metal ion is named. So these are the metals that form a single ion. They only have one charge. And this is group 1 is +1, group 2 is +2, group 3 is +3. Now it only highlights aluminum here, but gallium and indium would be in here as well. TL, I think that's thallium, but I'm not really positive about that. And guess what? We don't use that one very often. We don't even see gallium and indium very much. So aluminum is the important one. Then there are 3 others. Scandium is over here. Personally don't care if you remember that one or not. So just forget about him. But zinc and silver are important. Aluminum is +3, and then I think of going down the stairs. 3, 2, 1. So zinc is +2, and silver is +1. And we do need to remember those. The names for the ions of these elements are just the element name. So if we have Al3+, that's just aluminum ion. We don't change the ending or put Roman numerals or anything. It's just the same. Okay? Yeah. That's Mr. Volandi. He gets a little loud sometimes. All the other metals form more than one ion. And so then we have to find a name for these. So let's just look at iron because it's kind of a familiar metal. So here's iron. Iron forms a +2 and a +3 ion. So we can't just say iron ion because then which one are we talking about? So we use a Roman numeral in parentheses after the name of the element to identify which of the ions we're talking about. So the Roman numeral here, 2, means this is Fe2+. Iron 3 is Fe3+. Here's copper. Copper 2 is Cu2+. The nice thing is you don't have to know which ions they form. You just need to be able to match the name and the formula. So brief review of Roman numerals, in case you're rusty on those. So 1, 2, 3, 4, 5, 6. That's usually about as high as we need to go. So Roman numeral 1 is a capital I. And when you're putting these into mastering chemistry, the font is such that the capital I and a 1 look the same, and the lowercase l. But if you put ones in there, it's going to tell you it's wrong. And then you're going to be frustrated because it looks correct, but it's wrong. It's because you pushed the wrong key. So it's got to be a capital I. So 1 is capital I, 2 is 2 capital I's, 3 is 3 capital I's. Starting to look like tally marks. I'm going to skip 4. 5 is capital V. Okay? 4 is the number that's 1 before 5. And so it's IV. It's 1 before 5. And 6 is 1 after 5. So VI. And 7 would be VII too. Okay, quick review. There is also another system of naming that uses us and ick suffixes. And I want you to be aware that that exists because on a homework or a lab problem or something, it might give you one of these. And then you just say, oh, well, I'm just going to go look that up. I personally don't remember which is which. It's an older system, but it is still used. So we need to be aware of it, but you will not be tested on that. Okay? So here's some tricks to help you remember all of this stuff. So metals in group 1A and 2A form ions with a charge equal to their number. And metals in this triangle are also predictable. So in group 3A, we've got these 3 that form 3+. And then over here, there's 2 that form 2+, and 1 that is 1+. Makes a triangle. The ones in this triangle that you need to remember are these 3. The others might come up, but they won't show up on an exam. So groups 1A, 2A, 3A, zinc and silver, do not use a Roman numeral because they don't need one. All the other metal ions need Roman numerals because there's more than one kind. So let's think about the kings of England, right? King Henry. Which King Henry, right? There was a whole bunch of them. How do they distinguish them? Roman numeral after their name, right? There's King Henry IV and King Henry V. So we're doing a similar thing here with these metal ions. If there's more than one, we use a Roman numeral. If there's only one, we don't. Right? So my husband's name is Kirk Kawagoa. Pretty sure he's actually the only Kirk Kawagoa on the planet. So does he call himself Kirk Kawagoa Sr. or Kirk Kawagoa the First? No, because there's no need for that. Just Robert Downey Jr., right? There's a Robert Downey Sr. and a Robert Downey Jr., right? And so you need the suffix to tell which one of those are we talking about. When there's more than one, we use the Roman numerals. If we don't have to, we don't. Does that make sense? So I'm going to chant this to you, groups 1A, 2A, 3A, zinc, and silver, a lot. And by the end of the morning, you'll just be able to rattle that off. Groups 1A, 2A, 3A, zinc, and silver, no Roman numeral. If it's not one of those, put a Roman numeral on it. Any questions?
It says 1A, but silver is 1B.
So I'm not showing groups 1A and 2A in this picture.
Oh, so that's in addition to.
Yeah, this triangle is in addition to group 1 and group 2.
Zinc and silver. But it isn't also aluminum?
Well, that's the 3A.
Oh, okay.
Yeah.
Got it.
Group 1A, 2A, 3A, zinc and silver. Okay. So those are the cations. What about the anions? The anions are named based on their element names, but we just change the ending. They don't use Roman numerals or anything. We change the ending. So I have this place I've created. It's imaginary, and I call it Mrs. K's Chemistry Land. So in chemistry land, metals are masculine and non-metals are non-masculine. So they're feminine. So the metals use Roman numerals after their name, like men do in human society, and the non-metals change the ending of their name when they get together with a guy, when they get married, right? So we're talking like 1950, okay? We're just like super old school, traditional kind of stuff, right? So in 1950, a man and a woman get married, the woman changes her last name, right? So I think of all of these as being women, as feminine. And so when fluorine gets married, when she becomes part of a compound, she changes, she doesn't have a last name, she changes the ending of her name. Okay, so fluorine changes to fluoride, and that way we know she's married, right? Iodine changes to iodide, right? You like that, don't you? Phosphorus, phosphide. Now, with phosphorus and nitrogen, this part kind of comes and goes sort of randomly. I'm not going to try to trick you with that. Just watch out for it. The group numbers for these ions are predictable from the periodic table. Count backwards from the noble gases or group number -8. Okay? So, how do we name the compound? First, we're going to look at binary compounds. Binary meaning two. These only have two elements. So we've got a metal and a nonmetal, and you name the metal first and you name the nonmetal second. Just like in 1950, you're addressing a formal invitation, and it's Mr. and Mrs., right? You would never address it Mrs. and Mr. Why not? Because that's not how you do it, right? There's no value, judgment, or anything here. It's just tradition, right? And so this is tradition, how we always put the metal first and then the non-metal. So, KCl. Naming this, we look at the first element, K, it's a metal, tells us this is an ionic compound. So far we're only talking about ionic compounds, but still we should practice identifying them. So we're going to name the metal first and then the nonmetal. Well, K is potassium. We always have to ask ourselves, does it need a Roman numeral? Is it in group 1A, 2A, 3A, zinc, or silver? Yes. Just potassium, no Roman numeral. And then for chlorine, chlorine is getting married now. She's part of this compound, this married unit, KCl, and so she changes the ending of her name to chloride. So this is potassium chloride. There's a space between the two words. These are not proper nouns. They're not capitalized unless they're at the beginning of the sentence, and then you just capitalize the first one. Okay? CaO. Kind of looks like the Italian word ciao, except it's not spelled correctly. The first element is calcium. Is calcium in group 1A, 2A, 3A, zinc, or silver? Yes, it's in group 2A. Does it need a Roman numeral? No. Why? Because it always forms a +2 ion. So we don't need to specify which one it is because it's always the same, right? So calcium is just calcium. And then O changes the ending of the name, oxide, calcium oxide. Any questions? So let's practice a little bit. Name the compound Ag3N. Let's call him Steve. No, we have to use the systematic name. George. How about Augie? That would be a little closer. So we're looking at this, and we're seeing the first element is a metal, and so this is an ionic compound. We're just going to name the metal, and then the nonmetal. So Ag is the symbol for silver. Yeah, writing with the highlighter doesn't work so well. Silver. Is silver in group 1A, 2A, 3A zinc or silver? Why, yes, it is. It's silver. Doesn't need a Roman numeral. So, done. N, nitrogen. What does she change her name to? Nitride. Now, if you wrote nitrogide, I'd giggle and cross off the extra letters. Any questions? How about going the other way? We've got the formula, write the name. No. The name, right, you understand what I'm trying to say. Here's the name, we're going to write the formula. Well, rubidium. What's the symbol for rubidium? Rb. What's the charge on rubidium? 1+, because it's in group 1. How about sulfide? S for sulfur, and its charge is 2-. So how can we put those together? We need 2 rubidiums for 1 sulfur. If you're into math, this is finding the least common multiple. So we need 2 rubidiums for 1 sulfur. So doing it in a more visual way, if I put 2 rubidiums there, I'll have a total charge of +2, and the 1 sulfur gives me -2, and that's what I'm looking for, a balance between the positive and negative. Anybody have any questions about that? The nomenclature, especially ionic nomenclature, is one of those things that once you understand how it works, it's very simple. But until you do that, it's very mysterious, right? It's like one of those weird games with your fingers or different patterns, and you try to trick people. And once somebody sees the pattern, they can always guess the number you're trying to show, right? So that's what this is, except I'm trying to explain it to you. So then the book talks about the other kind of ionic compounds. Well, it's just the other elements, the other metals that need Roman numerals. So for these guys, the Roman numeral goes in parentheses, Roman numeral, and there's no space between the metal name and the parenthesis, and then this doesn't show it very well, but there is a space over here. We figure out what the charge on that metal ion is by looking at the charge on the nonmetal and the relative numbers of them by inference. So let's do this example. Name CrBr3. Well, the first element's a metal, and what's its name? This is chromium. Find it on the periodic table. Is it in group 1A, 2A, 3A, zinc, or silver? No. It needs a Roman numeral. So I'm going to put parentheses here. I don't know off the top of my head what it is, but I'm going to put the parentheses there, and I'm going to fill that in later. Br. Bromide, right? So we've got chromium something, bromide. But we don't know if this is chromium the first, chromium the second, chromium the 8th, right? We have to look at the charges to figure this out. So let's do that down here. So from the formula, I see that I have 1 chromium ion and 3 bromide ions. Yeah?
Why is it bromide and not bromate?
Why? That's an excellent question. Why is it bromide and not bromate? Because when you have a single nonmetal and she gets married, she changes the ending of her name to "ide." The 8 is when we get oxygen in there. Okay. So we have 3 bromines and 1 chromium. We don't know what the charge on the chromium is, but do we know what the charge on the bromide ions are? Yeah, they're each -1, right? So -1, -1, -1. So then the total charge from those guys is -3. That means the total charge from all of the cations put together must be +3. But there's only 1 cation, so it must be +3. Does that make sense? Draw them all out and do it like this if you need to. You do that a few times and then you can just kind of look at it and say, oh, well, that's got to be 3+. So this is chromium with a 3+ charge, and so its name is chromium 3. Yes?
Why are some of the compounds of dichromates?
That's a good question. Why do some of the ionic compounds have di in them, like dichromate? Because that's a weird one. Yeah. Most ionic compounds do not have prefixes like di and tri. There are some exceptions like dichromate. Because chromate is Cr(O4) 2-, and dichromate is Cr2O7 2-. And I'm not sure exactly why they chose to name it that way, but they did, and we just have to deal with it. But this is a good question. Anybody else have any questions? Pardon me? Mercury, yeah. Mercury's weird. Okay, so there's Hg 2+, and then there's Hg 2+. This is mercury 2. We're okay with that one. It's mercury with a 2+ charge. It's mercury 2. Mercury 1 is weird. It's Hg 2+. Why? I don't know. It is. There are some things that we just have to be okay with. So the good news is, I'm not going to try to trick you with this one on an exam. There are things I will try to trick you with, and I'll tell you, I'm going to try to trick you with this because I know that students get them wrong. And so I'm going to warn you, and a good half of you are still going to get it wrong, but then it's your own fault, right? Yes?
Is it because if you take mercury 2+, if you split it, it's mercury 1+?
Yes. So the charge on each of the mercuries would be +1. But what makes it weird is, why isn't it Hg+? Well, because every compound we see with Hg+, there's actually 2 of them. It's
Doesn't like
weird.
to be alone.
You know, they don't like to be alone. Yeah. And mercury's weird in some other ways too. It's a liquid at room temperature. Liquid metal? Yeah, weird. So those guys are weird. Name the compound FeS. Fester. Fe is a symbol for what element? Iron. I'm just going to point out it's iron. It's not iron. I started seeing students write like that. I'm like, what? And then I realized, well, that's more phonetic. Iron. No, it's iron. Is iron in group 1A, 2A, 3A zinc or silver? No. What does that tell me? It needs a Roman numeral. So I'm going to write the parentheses and figure out what the number is later. Okay? Sulfur is sulfide. So then off to the side somewhere, I need to look at these guys and see what the charge on the ions are. So I have 1 iron ion and I have 1 sulfide ion. And I don't know the charge on this one, but I know that sulfur is 2-. And if there's one of each of them, then the iron has to be 2+, right? Because the sum of the charges has to be 0, has to be neutral. So then this is iron 2 sulfide. Yes?
You would never write like iron 2 sulfide 2 minus, right? Because that's just implied.
Yeah, in the name, we'd never write iron 2 sulfide 2 minus or anything. We never put charges
In the actual,
in the name other than the Roman numeral, but it's not like a 2+ or something written up there. Yeah. So in learning how to teach this to students, I've sort of analyzed, because I like to, if I can't have a reason for something, I like to make up reasons. So I don't know if this is the reason or not, but it works for me. We're trying to be very concise and not write extra stuff. We're just trying to write the minimum amount that's necessary to communicate. So sodium chloride, we always know what the sodium ion charge is, so we don't need to put a Roman numeral. We're not going to. Here, we need to put a Roman numeral because otherwise we have no way of telling from the name if it's iron 2 or iron 3, because there's also an iron 3 sulfide and it has a different formula and different properties. Sulfide, this ending tells me it's the anion of sulfur and the charge I get from its position on the periodic table. Any questions?
It's not really on that topic, but why did they choose the ferrous iron?
That's a good question. So the Latin name for iron is ferrum. And so the old system of naming, there was ferric ion and ferrous ion. Which reminds me of Ferris Bueller. So why did they stop calling it ferrum? I don't really have a good reason for that. That's where the symbol comes from, Fe. Until relatively recently, science was a bit disorganized. People would discover elements and they would name them whatever they wanted to. And within the last, 100 years or so, IUPAC, the International Union of Pure and Applied Chemistry, people from different countries got together and said, okay, this is getting weird. Let's make a system that we all agree on and we'll go forward that way. And so I don't know if they decided to call it iron or maybe they took a survey and the most popular one, it was called iron. It was also called ferrum. In some countries, it was probably called something else entirely.
Another question is, why is mercury symbol Hg? I understand why.
Because its Latin name is hydrarga. So hydrogen, most of the first letters are all taken, right? And so they're looking for the first one that's like distinguishing it, and so they chose Hg. So most of the weird element symbols, there is some kind of a reason behind them, and they're often from the Latin or Greek names.
Wasn't Ag because they thought that there was silver in
Well, Argentina, Argentum, that could be. It's not an E, it's a U. So the Latin word for silver is argentum, and that's where we get the symbol Ag. And yeah, that could very definitely be related to Argentina. Yes?
Do you mind if I ask you like the other one?
I do not mind at all. This is a
What
lovely
the
tangent.
Antimony?
Antimony?
Or antimony,
Yeah, so antimony, SB. Yeah, I don't know that one off the top of my head. Is probably some Latin name that starts with S and has a B in it somewhere. Yeah. A lot of these, like polonium, germanium. Germanium was named after Germany. Polonium was named after Poland. Californium, named after California. The newer man-made elements, have, you know, some pretty serious discussions about who they're going to name them after. Some of them are named after scientists, like Seaborgium is named after Seaborg. Einsteinium, Fermium, Mendelevium, these are all named after people, right, who made notable contributions.
Stibium.
Stibium.
So that's why it's SB.
So I learned something today.
So most of them are named after, like, just a Latin term.
Did I do that right? Or is it Stibidium?
It's just, yeah, I just say Stibidium, but it's Stibium.
Stibium.
That's right.
So that's SB, we call it antimony. One of my favorites is W, tungsten. It's wolfram.
It's German, right?
Probably, yeah. Okay. We're going to pay for this later. Okay. Ruthenium 4 oxide. Write the formula. We need the symbol. Ru is ruthenium. And what does that Roman numeral tell me? That the charge on this ion is 4+. Ruthenium 4 means ruthenium 4+. Sometimes students think it's the subscript or something. It's related to the subscripts, but in a rather indirect way. It's just the charge. Oxide is O, and what's the charge? 2-. So the charges are not the same. One's a 4 and one's a 2. If you do the crisscross thing, you're going to have to simplify. If we think about this, I need 2 oxides so that the negative charges add up to the positive charges. So the formula here is RuO2. Questions?